Hello. Now we're going to work on concepts and strategies of ratios that will help us directly solve GRE type problems. So we're going to take a look at this pattern key again that we've built and notice a few patterns. One of the first things you'll notice is that every fraction has two parts to it. It has a top and a bottom. And a lot of times we think of fractions as just being a division problem, which that is one way of characterizing a fraction. But it's also important to notice the difference between the number on the top and the bottom. Notice over here how each of the top numbers is a count. There's 1/8, 2/8, 3/8. It's counting how many of the pieces we have. 4/8, 5/8, 6/8, and so forth. So the top is a count of how many we have, while the bottom serves a different purpose. The bottom is, while it's a number of divisions, what we really want to think of the bottom as representing is the size of the piece. And what you'll notice as the number in the bottom gets bigger, the size of the piece gets smaller because it's been divided more times. So a piece with a 16 in the bottom is much smaller than a piece with a 2 in the bottom. So the bottom gives us a representation of the size of the fraction itself in comparison to the unit it came from. And we're going to see that's a very important concept with fraction. It depends on the original size of the piece that we call 1. And through many of the problems, that size, that one piece will change. It will be either bigger or smaller. And then we can't compare fractions from different sources like that. Okay, so far, top is a count, bottom is the size. The bigger the number in the bottom, the smaller the size. The larger the number in the top, the count, means we have more of those pieces. Okay, so there's two sort of conflicting pieces of information there. The other thing you'll notice is that whenever we've got a fraction that has the same thing on the top as the bottom, that gives us a value of 1. So 2 over 2 is 1. 4 over 4 is 1. 8 over 8 is 1. 16 over 16 is 1. 6 over 6 is 1. Let's not forget 3 over 3, or 12 over 12, 10 over 10, 5 over 5, and of course 1 over 1. These are all different ways of writing 1. And we're going to see that means a completion. So along with this concept of making 1 is another concept, and that's the concept of a complement. In India, the mathematics that they came up with, which is really the mathematics we use throughout the world today, this idea of complement ran through all their calculations. It made their calculations easier to do. And we're going to take advantage of this because sometimes in a GRE problem, they give us a number, but we don't want to use that number. We want to use its complement. So we want to be able to get good at spotting complements because they'll give us the number that we don't use. We have to come up with the complement. So an idea of that, an example of that, is right over here. Change color here. So here's a fourth at the very top. There's 1/4. Below it is 3/4, and together they make 1. So 1/4 plus 3/4 gives us a complete number, gives us the complete 4/4. So these two numbers, 1/4 and 3/4, those are complements. So you'll see where sometimes we're given the number 1/4 in the problem, but what we actually want to calculate with is the 3/4, or the other way around. We could do the same thing if we've got 3/8. So this piece right here, what would be its complement? Well, the complement of 3/8 is what's left, is this 5/8. Because 3/8 plus 5/8 gives us back to the complete one, 8/8. So this idea of complements is going to be a powerful concept that will help us solving problems. The next one we want to take a look at is going to be this concept of equivalent fractions. So let's come over here where we have 2/3 and 4/6. We can see because they match up here that they are the same amount of space, the same amount of items, of area. But they're represented differently. So we've got 2/3 is the same amount as 4/6. And we could have chosen any other that equivalent fraction and we'd be fine. What we're going to notice about this is that there's this property that when we multiply across, cross multiply, so the 4 times the 3 and then the 2 times the 6. 4 times 3, we're going to find out that that's going to give us the same thing as 2 times 6. Yes, 12 equals 12. So this is going to form a strategy where we're going to solve problems when we have a proportion, two fractions that are equal to each other, but one of the fractions has something missing. So say we knew that one was 2/3 and the other was 4 somethings. We don't know this piece. And we will work problems at where this gets set up. What we can do is we'll see that you're going to cross multiply the ones that are across from each other, and then since we don't know what this number is in the bottom here, what we'll do is we'll take 4 times 3 and then we'll divide by 2. So watch what happens. 4 times 3 divided by 2. That gives us 12 divided by 2, which gives us 6, which we see from the previous example is the missing piece. So again, we're going to apply this and we'll see this worked out in GRE problems, but this alone will solve many of the problems we're going to be facing. Okay, so what else is there? Let me get some clean paper here because I want to find one last thing about fractions. So now we've got some clean area. So fractions is our percent. So you'll notice on your number key, which hopefully you still have out, but we talked about 2/10. And we didn't go any further in dividing past that, but if we did, we could have divided that tenth into 10 more pieces and gotten hundreds, and we would have had 2/10 would be equivalent to 20 hundredths. This is the basis of the concept of percent. The per part means divide. So whenever we see the word per in math and in these problems that we're doing, we're going to think of division. Cent is a Latin word meaning 100. So it's divided by 100, and notice that's exactly what's happening. So a percent is a fraction. It's just it's a way of consistently having a consistent fraction that's always divided by 100. The denominator is always 100. So let's take a look at something like 23 hundredths. Okay, what does this mean? Well, if we take 23 divided by 100, and let's verify that with the calculator here. Looks like I did that earlier. You take 23 divided by 100, and we get its decimal equivalent. So when we're doing math, we're going to see that we can take 23 divided by 100, or we can take 0.23. These are two numerical ways to write the same concept. A non-numerical way to write this, and again it's strange because it's using numbers, but what we do is we also write 23 over 100, or 0.23. We can write this as the number 23 and then put this symbol on it, percent. Now let me highlight what that symbol means. The two little O's here and here come from the zeros in 100. And the bar, this thing here, is a symbol for division. So it's literally meaning 23 divided by 100. But what we've done now, this is really no longer a number, it's a label, it's a name. It's something we can't do math with, but we can represent an answer as 23%. Okay? If we're going to do the math, we're going to need to use either one of these forms, and what we're going to find is probably the form of the decimal is going to be the most beneficial. Finally, when we're talking percent, what's complete? What do we have when we have everything? Well, we have 100 out of 100. That's complete. What if we were to increase by a certain percent? Say we increase by 23%. Well, that means we got more. We've got what? 23% more. That means we've got 123%. We've got what we started with, and we added to that. And we're going to see that that will give us a decimal of 1.23. My calculator out here just to prove it. 123 divided by 100, 1.23. Okay. The same concept applies if we go to decreasing. So again, whatever we started with everything. We started with 100%. And let's say we give a discount, or we reduce the price, or something goes down, we lose some members, let's say 15%. Or 15 hundredths. Well, that's taking the 100, subtracting 15 from it, and so what do we end up with? When we're decreasing, in this case, we'll end up with 85 out of 100, which again, in a calculation, we'll use the number 0.85. And we're going to do this in some applied problems, but you'll be seeing us, one of the strategies will be basically to go directly to these kind of numbers. When I see 15% decrease, I'm going to think of 0.85, 85% is what I get. When I see 23% increase, I'm going to think of 23 plus 100, 1.23 is the number I'm going to use, 123%. Okay, so we'll get some practice with this, and this will speed up our calculations because we not only want to be correct in our answers, but we want to pick up some speed because when we take the GRE, it is a time test, and we'll have a limited amount of time to spend on each problem. And the more we pick up the speed, the more confident we'll feel, and the more questions we'll be able to answer correctly. Okay. That's all I've got for this particular setting. So let's move on now to the problems, GRE problems, applying these concepts. And we'll probably get a few more as we go, but these were the 5 sort of main concepts I wanted you to have in mind as we go on to the next step. Thank you.